All right, now let's get into the fun stuff. And I don't mean that sarcastically, I actually love this stuff. So, I'm going to start talking now about what the course, we've reviewed basically, hopefully everybody at the same level for their background. Now let's talk about analysis variance. This is we're going to do this till sometime in March. All right. So we've done t-tests and z-tests. We talked about those. We've talked about those in the classes. And they're either one group difference from a population mean or two groups from each other, which of course technically is two groups, one minus the other, minus the two population means, but you know what I mean. So it's differences with one or two groups. What if we have more than two groups? So if you have more than two groups, there's a potential problem. And that problem is that, like, if you have this example here, this is a variable called A. It's got three levels, A1, A2, A3. This looks a lot like your assignment. It's posted on my website. It's due a week from today. Yeah, Thursday. Except it's got four levels of A. And the question I ask in that assignment is there an effective A? All that means is, do any of the groups differ from each other? Okay? So, there's one way you could answer that, which is by doing, in this case, what? 1, 2, you can do 3 t-tests, I guess. Right? You could. You have a potential problem there, which is the alpha goes up, but you could do it. With 4 groups, you have A1, A2, A1, A3, A1, A4, A2, A3, A2, A4. Yeah, at least 5. Well, I'm not keeping track of that very well. But suddenly we got all kinds of testing. It's not good. So we got this, I don't know what this is. Who knows? I have no creative abilities whatsoever, so I don't know what this is measuring. Looks like marks on a test. Let's pretend that's what it is. I don't know. The question you ask yourself, of course, or one can ask oneself, is why do scores vary? Well, and the other way to put this is what are the sources of variation, which is something we're going to talk about. You're going to be so tired of me talking about sources of variation. Too bad, it's a required course. So, what are the sources of variation? Well, first thing that comes to mind is individual differences. Right? Even if it was just 2 groups here, and it's you people here and you people here. Or a couple of you over here to make the group sizes equal, but whatever. Everybody here is different. Obvious source of variation. And of course, the differences between the groups. So if again, if we were just doing it with 2 groups, which is the left and right half of the room, one of the reasons you're going to score differently on whatever the hell this is we're measuring is you're different people. Just look around, don't all look the same. The other reason is that you're put in different groups, and maybe there's some special thing on the left-hand side of the room that I've done without your knowledge. So who knows what it is? But whatever that is, there'd be a group difference potentially as well. And really, that's our question. Is there a group difference or is there not? We know there's individual differences. There always will be. Right? No matter what you're measuring. Right? If you're measuring anything in some kind of life science situation, you're always going to have individual differences. Right? So any score has a baseline level of being human or rat or chickadee or plot of land, if you prefer. So there's a baseline level just because you're you, because you're H sapiens sapiens. Then we can add in group differences, which is this part of the room or this part of the room. Or A1, 2, 3 in our example, or 1, 2, 3, 4 in the example on the assignment. And then we have individual differences. Right? That, I don't know, that one's different from Mark, is different from Shane. Different people. So those are our sources of variation. Well, this thing actually doesn't vary. Everybody's got a baseline level. And again, it can be human, it could be anything. It doesn't matter what your subjects are in your experiment. There's a baseline level. And then there's the group differences and individual differences. Okay. Questions so far? Do you have any questions for me? Because what I said so far made some sense. You good? Okay. Let's move on. Oh, well, we can make that into, you know what all that is? I'm just turning this into this. Like, it's shorter to write x equals mu plus tau plus epsilon. Mu is the grand mean, tau is the treatment effect, epsilon is the error or the individual differences. X equals mu plus tau plus epsilon. It's just a way to write it out that doesn't mean I have to write all this crap out. I can just use a few Greek letters. Okay? What we're doing here is we're building a model of where our data, where the variance in our data comes from. So we're saying this model is sensible, so let's figure some stuff out with it. But you see why the model is sensible? Grand mean plus treatment effects plus individual differences. X equals mu plus tau plus epsilon. Okay. So that's actually called the structural model of analysis of variance. There it is again, x equals mu plus tau plus epsilon. Any score equals the grand mean plus the treatment effect plus error. And error just means individual differences. Error is something we don't measure directly. It's there because people are different. It's there because rats are different. It's there because black-capped chickadees are different. That's all that is. Okay. X equals mu plus tau plus epsilon. So now let's break this down a bit. Let's make some assumptions. First of all, let's say all our groups are equal. It's the HO assumption, the null hypothesis assumption. We always start with that. We try to show it's not true, but we start assuming that nothing happened, right? So we're saying that mu1 equals mu2 equals mu3 equals ... mu k. There are k groups. There are k groups in our experiment. And we're saying that all the means are equal. It's the null hypothesis. We're saying HO is true. If HO is true, and the means are all the same, the variances are all the same. Right? They all come from the same. What it's saying is mu1 and mu2 and mu3 and ... uk are actually all the same distribution. So they therefore all have the same variance. Sigma squared sub 1 equals sigma squared sub 2 equals ... sigma squared sub k. Make sense? Okay? You good so far? You have to ask questions if you don't get this, because this is like underpinning the rest of the course. No pressure! Okay. Oh, yeah, please.
So do we assume that they're all equal every time?
Yeah. Think about it. We do that with each standard t-test. We assume it's not equal, and then we prove that it is, that that's wrong. Right? So we assume that HO is true with a t-test. And then we say, what's the probability that HO is actually true? Oh, really unlikely. So it must not be true. We always start out by assuming it's not true. It's an easy thing to assume, too, because when we talk about power, how hard it is to assume, there is an effect on how big it's going to be. Assuming HO is easy, right?
What's the K mean again?
K, there are K groups.
Okay.
It's just an index.
Okay.
K goes from, J goes from 1 up to K. So J is the subscript. Mm-hmm. J equals 1, J equals 2, J equals 3, ... J equals K.
Okay.
Yeah. Thank you for asking. Other questions? So we're starting out by just assuming the null. Standard assumption, nothing to be afraid of. It's just a null hypothesis assumption. It's always made in sort of classical inferential statistics, which is what we're doing. Okay, it was good. It was good. Excellent. We're going to assume that scores are randomly and normally distributed around the grand mean. So they're random. The scores are a random variable, meaning if I know any score, it's just random, but it's around the grand mean. So we put a restriction on it. And it's normally distributed, so all the scores together are normally distributed around the grand mean. That sounds kind of tenuous. We can kind of violate that and not worry. We do this for the math that's behind it. It makes the math easier. It makes the math work. But you can violate the crap out of this, out of most of this. The being normal doesn't matter really. But saying it's normal allows us to do some math in the background that you don't have to worry about. We can't violate this. The observations are independent of each other. So if I know Simran's score, I don't know Cheyenne's score. It tells me nothing about it. Literally nothing. They are dependent on each other. Okay? Independent observations, that cannot be violated. And think about it. Our model says x equals mu plus tau plus epsilon. It doesn't say also it depends if you're sitting beside an element. There's nothing there. Right? That's a safe assumption to make, first of all, if you design your experiment properly. Secondly, you can't violate this. And think about it. If you design an experiment testing group differences, would you want there to be any dependence between scores? Well, no, you wouldn't, would you? What would you be able to say if you said, like you wouldn't want to say, well, these two groups are different unless it's Thursday at around 11:40. You wouldn't want that. That's not good science. That's weird, shitty science, which was a movie just called Weird Science. It was called Weird, Shitty Science, which is not nearly as good as I remember it being when I was 18. Doesn't hold up well. Anyway. Yes, I'm referencing Weird Science. Anyway. Oh, all the sources of variation in the model. That's a reasonable thing to say. There's nothing extra hanging around that's causing the scores to vary. It's x equals mu plus tau plus epsilon. Okay. So these are reasonable assumptions. We can't really violate that either. You know what? The nice thing is if we violate any assumption of these two assumptions badly, it makes the test more conservative. It makes it less likely to find a difference. So at least you're less likely to say something stupid in print. It's still going to happen, but it's less likely. Design your experiments properly, these won't be problems. And like I said, the first time we can violate this here. It's no big deal. Okay. Questions? Okay, so if you accept all these assumptions, please go ahead.
So like, you know with the so the t-tests are for the two, like if you're comparing two groups.
Yep.
And for those, like you couldn't have the simple, like they had to be random samples.
They kind of had to be.
For the B's?
You can violate the crap out of the simple
okay.
random sample too.
Okay.
Yeah, the beauty of it is you can violate that. In fact, we violate it all the time, right? I mean, you're biology, right? Yeah. What kind of stuff are you interested in?
Medicine.
Okay. What kind of research stuff are you interested in?
I don't know.
Like you're going to do your thesis next year? Or?
I don't know yet.
Okay. But I mean, think about a paper you've read.
Okay.
Right? Have you read any Jen Foot stuff about the birds and the singing and such? Yeah, that's a good description of Jen Foot's insert funded research. It's about the birds and the singing. But she does really great stuff on like social signaling and birdsong. And she analyzes data using these kind of techniques. Do you think she randomly samples the black-capped chickadee she has from all over the world? Well, no, of course not. Yet it still works. And the reason we know it works is because we can do something called a Monte Carlo simulation. So I can set up a simulation making it non-random, making it non-normal, making it not sampling. It still works. Because when I set Monte Carlo simulation, I actually know the differences, right? I set that up and I screw with it, and I do the analysis, and it comes out almost exactly the way it would, even though I violated those assumptions. I violate the independence one, I'm dead. I violate the other sources of variation in the model, I'm dead. But I can violate the randomness. It's a really good question, by the way. Yep, a really good question. I like the fact that anybody who wants to go to medical school is interested in just taking an extra statistics course. Thank you. Later in the term, I will tell you about doing consulting, statistical consulting with a group of ophthalmologists when I was in graduate school, and how I had to tell them they wasted all their money, and I now have my $200. Anyway, let's look at the variance. Now we're going to do let's get a little mathy. Not a lot mathy, but a little mathy. Sigma squared sub 1, which we don't know. The group variance for group 1, we actually don't know it. We can guess it. It kind of equals, it equals approximately. That's what the wavy equal sign means. It equals approximately s squared sub 1. Because s squared is an unbiased estimator of sigma squared, yes? Okay. Sigma squared sub 2 it roughly equals s squared sub 2. And so on. Right? That's just good. Sigma squared sub epsilon, that's in other words the variance due to individual difference. Should equal s squared for the whole thing, shouldn't it? Because we made a null hypothesis assumption. We said there is no treatment effect. Therefore, all variance is because of individual differences. If that's the case, sigma squared should equal, s squared should equal sigma squared sub epsilon. Because the only variance we have is in the individual differences. Because we've assumed the null. Does that make sense? Yeah? Okay, because we said there's no treatment effect. We're assuming the null. If that's the case, then the average variance for each group, J just means group. So I go from group 1 and group 2 and group 3. I add all up, all the variances, up to group K. And I divide by the number of groups, which is K. I will get the average variance of each group. You say, Dave, you're taking average variances. And my answer to you is this. The numbers don't know where they come from. They don't care that I'm taking an average of a bunch of variances. So s squared sub j divided by k. We're going to sum that, and we're going to get s bar squared sub j. In other words, the average variance of each group. In other words, your variance and your variance. We add them together, we divide by 2, and we have the average variance. That's all that is. That should be an estimate. An estimate, of course, because it's a stat, not a parameter. It should be an estimate of sigma squared sub epsilon. This guy right here. Hello? I always wonder why there's phones in the classrooms. I've been tempted to call for a pizza. Get very hungry and this time. We were in a pizza or a chemistry class in grade 13, grade 12. Just like the fast times usual. It's great. I was such an idiot in high school. Anyway, any questions on this? Does this make sense? This should be true, assuming all the things we are assuming are also true. Okay, so that's one thing. By the central limit theorem, remember there's going to be, I kept saying, you know the central limit theorem, it is important. By the central limit theorem, the variance in x bar, remember that's a sampling distribution of x bar, equals sigma squared over n. That's just a thing. Take that as a given. It's a known thing. It's from a theorem, from the central limit theorem. It's the variance of x bar equals sigma squared over n. Well, the variance of x bar, that's s squared sub x bar. It's the same thing, isn't it? I just changed var to s squared. So if I took the variance of x bar, your mean, everybody here, and your mean, everybody here, and I took a variance of a bunch of means. You say, Dave, you took a variance of a bunch of means, and my answer again is the numbers don't know where they come from. S squared sub x bar should equal sigma squared sub epsilon over n. You say, but Dave, you substitute sigma squared sub epsilon in for sigma squared. Yes, I did, because we're assuming the hypothesis is true. So I can just throw that in there. And now I can isolate sigma squared sub epsilon by cross multiplying, and I get sigma squared sub x bar times n should equal sigma squared sub epsilon. So sorry, s squared sub x bar times n should equal sigma squared sub epsilon. Okay. Take a look at that. Ask me questions about it if you have. Yes, please.
On the slide before this one,
Yes.
how come the one S with the J has a -2 as the?
Is it -2?
I think you meant
No,
it's
it's
2
2
bar. Oh, it's just 2 bar. Okay.
Yeah, okay. Oh, sigma squared bar, yeah. So it's the
Okay.
average, or s squared bar, it's the average variance. So it's this variance plus this variance, divided by, well, in our case here, 2, k would be. Good, thank you, because the notation can be annoying. And especially if you haven't played math in a while, notation can be really annoying. And especially if it's Dave Broadbeck's somewhat proprietary notation. It's proprietary. Other questions? So far, you may not know where we're going yet, but you're still on the bus with me? Okay, a strange metaphor. Why did I do that? Well, I did it, and I say I, R.A. Fisher discovered this, because I have now two independent estimates of the same quantity. I have two estimates of sigma squared sub epsilon. This one here, sigma squared, the sum of s squared sub j over k, where j goes up from 1 up to k, and s squared sub x bar times n, both should equal sigma squared sub epsilon. So the average variance, your variance plus your variance, the average of that, should equal the variance of your two means. They should equal the same quantity. They should equal the same quantity. How did my shoe come tight? They should equal the same quantity. That's mean square treatment. That's mean squared error. So when you first learned about analysis of variance, you've all learned that, right? If you took the psych stats or you took the biostats, you've learned about analysis of variance, right? And you were told this is mean square treatment, this is mean squared error. And then you probably thought, that's good. Why is that? And then you know. The more you know. So if HO is true, the expected value of mean squared error should be sigma squared sub epsilon. And the expected value of mean squared treatment should be sigma squared sub epsilon. Or I like to, now this is sort of Dave notation. HO true, HA true. And we're going to go expected value, mean squared error, expected value, mean squared treatment. So they should both be here. So I just like to say that epsilon and epsilon. It's actually, for me, it's useful because I know we're referring to error. I just need to refer back to the model. So that's what I will typically write. Technically, it's sigma squared sub epsilon, but I just write epsilon. Okay? So those two quantities, even though they're calculated separately, one is I take the variance of your two means, and the other is I take the average of your two variances. They should be the same if there's no difference between the groups. Right? They should be the same if H is true. HO is not true. the expected value of mean squared error remains the same. But the expected value of mean squared treatment, which is the variance of your mean and your mean, should also include group differences, shouldn't it? So within each group, it's not going to include group differences, because there's no group difference effect within a group. But between two groups, it should be different. So now we have an effect of treatment, and it's actually technically n times sigma squared subtreatment, sub tau. I just write this as treatment plus error. Okay? And well, mathematically, I'm just using the shorthand, sort of the Broadback shorthand. So a math professor would tell me, that's not correct, and I'd say, well, yeah, but I'm not a mathematician. I'm doing this conceptually. Mean squared treatment should measure treatment plus error, or error. And mean squared error is always just measuring error. So the expected value for mean squared error is always less than the expected value for mean squared treatment, if HO is not true, if HA is true. Questions? Does this make sense so far? Okay, I'm very excited. Or you're completely dumbfounded. But I'm really good at this, so I think you'll get it. You realize I'm kidding, right? Though I am really, really quite good. Okay, so. In fact, my next slide is entitled So. You think I might have taught this course before. So, if we were to divide mean squared treatment by mean squared error, by the way, the notes, I had it wrong for years, I finally fixed it. So if you downloaded notes or something, there's a mistake, now it's fixed. Ha! I shouldn't be that excited about changing a couple letters, but I've been planning to fix it since 2006. It's only taken 14 years. I've finally done it. Mean squared treatment divided by mean squared error. And again, if you have the old notes, it says mean squared error divided by mean squared treatment, that's wrong. We would have some estimate of how much extra variation mean squared treatment is measuring. We would have some extra measure of variation. In other words, we have tau. We want to know if that's not zero. Oh, cool. Let's find it if that's non-zero. If that's non-zero, we have an effect. Now, because of the way of sampling error and stuff, it has to be enough non-zero, right? But right now, we're doing this on a purely theoretical level. So as long as it's non-zero. So we're going to have tau, our treatment effect. This is precisely what is done in the analysis of variance. And we do division rather than say subtraction. Subtraction would work, it would give us a number, but it wouldn't be standardized. When we do division, we can say, well, it's standardized, doesn't matter how big mean squared error is. So F equals mean squared treatment divided by mean squared error. Okay. What's the expected value of F if HO is true? Please, Mark.
1.
Yeah. Because what? It's epsilon. Well, what is F? Using my notation here, F equals tau plus epsilon over epsilon. If tau is 0, we have epsilon divided by epsilon. Epsilon divided by epsilon is 1. What is it if HO is false or HA is true? Someone other than Mark. What's it going to be? So it's tau plus epsilon over epsilon. What would we expect that to be if HA is true? Soon I shall force someone to answer. So just guess. Please.
Would it just be tau?
But, so remember, it's tau plus epsilon over epsilon. So what is that going to be if tau is non-zero?
More than 1.
More than 1. It's got to be greater than 1. Yep.
Anything but?
It's greater than 1. It can't be less than 1.
Okay.
Because those are squared quantities, they're variances. Sometimes it comes out less than 1. What would the hell would mean? How? What? How's that? Because you violated an assumption. Usually that's an assumption violation. That means the math behind it didn't work properly. Okay. So if HA is true, it's greater than 1. If HO is true, it's just 1. It can never be less than 1, but sometimes you do get obtained F values that are less than 1. You calculate when they're less than 1. You think, how the hell did that happen? And that happens because you violated an assumption. Usually an assumption called homogeneity of variance, which is that all the variances are the same. So if HO is true, then MST, mean square treatment, divided by mean square, will be distributed as an F with degrees of freedom for treatment and degrees of freedom for error. If not, it will be distributed some other way. So this is why you look it up in a table to see if there's a difference between the groups. Yes, please.
So if we get a number that's lower than 1, do we assume that HO is true? Or do we have to
Oh, you will always, that would never, a number less than 1 would never be greater than the critical F value. What you can, depending on how much it's less than 1, if it's like 0.8, don't worry about it. But if it's like an order of magnitude less than 1, like if you're starting to get 0.08, not the p-value, the actual obtained F value, that's a problem. That's, you violated an assumption, and you violated the crap out of something. Because that said, all this stuff we just said isn't true. And while, like all the math that I just said, so this is this, and this is this, that says none of that's true. Well, that all had to be true. And the only way that is not true is if those assumptions are false. If those assumptions are false, then none of the math works. Yeah.
Is the DF degrees of freedom?
Degrees of freedom. Yep. And I see it a lot. I'll tell you something. The number of people who get really happy, oh, there's no effect. This part I expected, no effect. Look, my F value is 0.01. It's like, dude, do you know that you did it wrong? And this is, I'm not talking about just undergraduates' thesis research projects. I'm always the jerk at the thesis conference that says, think you violated homogeneity variance? I usually do that before the thesis conference, they know it, but papers by colleagues, yep.
So what do you do if it's less than 1?
We talk about it on Tuesday.
Oh.
Yeah, they'll always be fixed. Oh, usually, not always. Sometimes you stop using this test, use a different test, use something called a Kruskal-Wallis non-parametric F test, which we're not going to talk about this course. But it's a trivially easy thing to do. But yeah, if you violate the assumption too badly, you have to try to fix it with the transformation, or don't use this. People get really married to F's and to T's. They're really excited about F tests and T tests because they've learned about them in school. Right? And then sometimes it's just not the appropriate test. In fact, when I was a postdoc, I was I was being paid to analyze data. And it was a woman who had a master's project, and it was on, her advisor was cool doing it, on sexual behavior in bonobos. You know what bonobos? Little chimpanzees that are sex machines.
Oh, don't they have it like every few minutes or something?
Yeah. The bonobo handshake is sex. Only other animal probably has sex for fun, other than humans. So they're fascinating animals. Anyway, so she's studying this stuff, and she doesn't know how to analyze her data. So I got all the data, I figured out how to do it, and then her dad calls me. It's like, I'm 28 years old, and her dad is calling me. Well, wouldn't it be more appropriate to do a t-test? I said, how would that work? And the guy is dead air on the phone. I said, your daughter's paying me because I'm an expert in this. Are you an expert in that? Oh God, I was such a dick. Are you an expert in this? Oh, blah, 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 blah. I have an MD. I said, I have a PhD. I teach statistics. T-test, blah, blah. I said, no, your daughter shouldn't come to you for advice on stats. Maybe if she's sick. God, I'm such a jerk. I wouldn't have said that if it was like, he was sensible, but he was like trying to tell me how to do. This is, by the way, probably what it's like being a woman. A man just tells you what to think. No, I don't know about that video because I'm taller and speak louder. This guy was MD explaining me stats. It's great. All right. So, now we have to figure out the whole degrees of freedom deal. What do we do? Okay, sum of squares. Remember, these are sums of square deviations from means. The sum of squares total equals the sum of squares treatments plus sum of squares error. And the degrees of freedom, the total, any design is a finite number of degrees of freedom. The numbers can vary a certain amount. Is the degrees of freedom for treatment and the degrees of freedom for error. I, by the way, don't think my experience is like that or anything like it's like to be a woman. I'm just making a joke. It's appalling. You want to get treated anyway. So let's be more precise. Okay. The sum of the variation of each score minus the grand mean, that's the overall mean. That's the total sums of squares. Yes? And that equals x bar sub j, what's that? Group 1 and group 2 minus the grand mean. So your group mean and your minus the grand mean and your group mean minus the grand mean. That's all that is. Okay? So I know it looks weird, but it's sigmas and j's and k's. Don't worry about it. The important thing is the total, which each score minus the grand mean equals your mean minus the grand mean plus your mean minus the grand mean, and squared, right? And then plus your square minus your group mean plus your square minus your group mean, squaring all these. Your square minus your group mean squared, your square minus your group mean squared, your square minus your group mean squared, and then your square minus your group mean squared, your square minus your group mean squared, and blah, 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 blah. And then why are there two summation signs? Because I'm going to add this whole quantity that I got to this whole quantity that I got. That's why there's two summation signs. I didn't put the indices in because it just, I hate working with the equation editor. That's mostly why. It's mostly that. Okay. Did what I just said make some sense? That's all that comes from. That's means sum of squares total, sum of squares treatment, and sum of squares error. Or sum of squares, sometimes called between groups and within groups. You'll see that. They mean the same thing. This has n minus 1 degrees of freedom. Big N, total number of observations in the experiment. What do we have here? 15, that's an odd number. No, we have 60 in this group. 15 minus 1, or 60 minus 1, 15. This is k minus 1 group. So we have two groups. K is 2 minus 1 is 1. And then this one here has big N minus k. Our big N is 16. K is 2, so that's 14.
So who's the number of groups?
Yeah. So if you were to calculate this by hand, and you know what? The first ANOVA assignment, the one that we have that's due next Thursday, you could actually do this. I wouldn't. I would do it by computer. But if you want to try it, it's quick enough. Like there's only 16 observations. It's a pain. It'll take you like 40 minutes of screwing around your calculator. But one could do it. When the designs get kind of big, you can, but you can't make mistakes. But you could do it by hand. You can do this exercise by hand if you want to. I wouldn't do it by hand. I'd use a computer. So that's mean squared treatment, mean squared error, or sometimes mean squared between groups, mean squared within groups. Call it that if you want. And you get what's called an analysis of variance summary table. And you'll see this when you get your output from your stats software, whatever you're using. You'll have source of variation, degrees of freedom, mean square, and F. Degrees of freedom, K minus 1, within groups, between groups, within groups, or it could be treatment and error. It could be treatment and individual differences, it might say. All kinds of possible different things. But it's always going to be in this order. Sum of squares between groups divided by, or also called sum of squares treatment, divided by K minus 1. Sum of squares within groups, or sum of squares error, divided by big N minus K. And then the F value, mean squared between groups, divided by mean squared within groups. And then you look to see, of course your software will look to see, but if you do it by hand, you will look to see if the F value you get exceeds a critical value. If it exceeds the critical value, you reject HO and you say your groups are different. Okay? So the thing is, our null hypothesis, let's say for the assignment has 4 groups, is that all 4 groups have the same mean, are the same. If we reject HO, it just says that 2 means are different. Doesn't say which 2. Doesn't say that all 4 means are different. Doesn't say 3 means are different. Doesn't say which 3 means are different for all 3. It says 2 of them are different. We don't know which ones. So that's something you got to keep in mind. That, no, for us, for 2 groups, well, obviously, it's these 2 groups that are different. Because there's only 2 groups. But as soon as you have more than 2, you don't know which 2 different. We'll also talk about that.
So if there's just 2 groups, is there a difference between writing a t-test and this?
No. No, this is, in fact, they're intimately related. And in fact, the final question of the assignment, you will tell me how. I'm not going to tell you how. You should be able to look at it and think about it a little bit and try to figure it out. But yes. So all you do then is you find, does it exceed a critical value? So it's not just, is it greater than 1? Is it greater enough than 1? I'll show you a set how to do this on the computer. It's really very straightforward. The hardest part of any of this stuff is always setting up the data set. Once you've done that, you're cool. So I'll show you that in just a second. Do you have any questions before I stop recording this? Good? Okay, I'll show you this, how to do the assignment.